Welcome to the Abbey Road Observatory. I'm your host, Jim, the filter guy. I'm here today with an assortment of filters. We have a Bader Moon and Sky Glow, an Antares Variable Polarizer, kind of a no-name brand color correction, Astronomic UV-IR cut, a couple of different white light solar filters made with Bader solar film. These are all what I call special filters, and that is the topic of today's video. Before we get into my presentation, if you like what I've been doing here on the ARO, why don't you hit that like button down at the bottom of your screen, and if you want to keep up to date with everything that's happening at the ARO, click subscribe. Alright, let's get on with this part 3 of my Understanding Astronomical Filters series, Special Filters. Welcome to part 3 of my 4-part video series on Understanding Astronomical Filters. In this video, I will discuss what I call special filters, those that do not fit into the two common categories I already discussed in the first 2 videos, namely color filters and light pollution filters. Part 1 of this video series discussed what are astronomical filters, how are they made, etc. Part 2 discussed how to choose the right color and light pollution filters and how to use them. In Part 3, this video, I will discuss the following special filter types: UV-IR blocking, neutral density, planetary observing imaging, special color, neodymium, chromatic aberration correction, and solar filters, including white light and extremely narrow band. Part 4 of this video series will discuss some advanced topics such as extremely narrow bandwidth filters and use with fast optics. In general, filters all draw upon the same technologies, as I've discussed about the other filters in the previous 2 videos. They use a combination of absorption and reflection to achieve their desired spectral response. They are designed to fulfill very specific tasks, which can sometimes mean that they don't see a lot of use, depending on your observing patterns. Because of their specific applications, there also does not tend to be a lot of manufacturers of these special filters, and as a result, they can often be rather expensive. The first special type of filter to discuss is the ultraviolet, infrared, or UV-IR blocking filter. This type is intended for imaging only, since the human eye is not sensitive to these wavelengths of light. UV-IR blocking filters are used to pass only the visible spectrum, resulting in sharper and better focused images. This is so because many lenses or telescopes are designed to properly focus only visible light, not UV and IR as well. Included in this group are so-called color correction or CC filters, whose purpose is to modify the spectral response of a camera sensor to be more like the human eye. The blue and magenta curves on the plot at right are both spectra for commonly used color correction filters. All commercially available digital cameras have some sort of CC filter installed. Unlike the other special filters I will discuss in this video, UV-IR cut filters are very common and are readily available from many different retailers. A word of warning, however, that many of the available filters have poor response to the important wavelength of hydrogen alpha at 656 nanometers. So before you buy one, you should confirm what sort of response the filter provides. Of the UV-IR blocking filters that I have encountered, the Bader Planetarium brand filter is one of the better performers.
The next type of special filter to discuss is the neutral density filter. This is a purely absorption type filter whose purpose is to attenuate the brightness of the object you are observing uniformly across all wavelengths. They are available in a variety of optical densities, or OD, meaning you can usually find the right filter for your application. The luminous transmissivity, or %LT, of a neutral density filter can be calculated from its optical density using the following equation. %LT equals 10 to the power of negative OD times 100. So for example, a filter with an optical density of 0.6 has a %LT of 25%. It is attenuating the light passing through it by 75%. Another option for reducing the brightness of what you are observing is to use a variable polarizing filter. This filter is in fact two linear polarizing filters stacked on top of each other. As you rotate one filter relative to the other, you change how dark the filter is. Many observers prefer the flexibility of a variable polarizing filter over having a selection of ND filters with varying optical densities. The next filter category of special filters to consider is that for planetary observing. As discussed in Part 1 and Part 2, astronomers commonly use color filters in an attempt to darken planet surface features and make them more visible. By applying interference coating technology to this problem, i.e. reflective type filters, unique filters that accentuate multiple surface features simultaneously can be created, something a simple absorption type filter doesn't normally do. There are a number of planetary contrast enhancement filters available commercially. Some have their spectra plotted there on the right. Most of them are designed specifically for improving the view of Mars. In my experience, these filters work, but some better than others. Just like with the use of simple color filters, the improvement is very subjective. Of the filters I've tried, none stand out as being all round better than a simple color filter. I also have a general caution regarding the transmissivity of these filters. Some of them cut a very large percentage of the incoming light, making them unsuitable for smaller aperture telescopes. For example, the Orion Mars filter I personally found to be too dark to use with my 8-inch SCT. For those interested in imaging the planets, there is another special filter category that may be of interest. These filters take advantage of the fact that cameras have a wider spectral response than our eyes. This opens up an opportunity to image the planets using wavelengths of light we can't normally see. Infrared pass filters are very popular because of their ability to steady seeing conditions to provide sharper images. They can also be used to take views that are not visible in other wavelengths of light. I especially like to use an IR pass filter when imaging the moon. I talk a lot more about imaging with IR pass filters in my video, Seeing Beyond the Visible, if you would like to learn more. UV band pass filters are also popular for those interested in imaging structure in the clouds of Venus, or for imaging different distributions of elements in the clouds of the gas and ice giants. There are few vendors of UV bandpass filters, so they tend to be expensive. Somewhat related to special planetary filters are special color filters. There are two main groups of special color filters, those meant for studying star brightness and those used for color imaging with a monochrome camera. The first group are meant for those pursuing the study of star brightness called photometry. By observing stars using a selection of very specific bandpass filters and comparing the observations to calibration stars, one can determine the star's spectral class, temperature, and other useful properties. The most commonly used filter set for photometry is the UBVRI set, the letters denoting the color of each filter in the set, so ultraviolet, blue, visual band, which is centered on green, red, and infrared. These filters started being used for the purpose in the early 1950s by professional American astronomers Harold Johnson and William Morgan. Back then, the set only consisted of U, B, and V filters. R and I were added by South African astronomer Alan Cousins in the early 1990s, after the invention of red-sensitive photomultiplier tubes, which were the device used up to that point for photometric studies. The UBVRI filters are all absorption type, but have very specific formulas so that photometry measurements taken by different astronomers using different brand filters can be directly compared with each other. A more modern version of these filters are modeled after those used for the Sloan Digital Sky Survey, which are interference type. Note the flat passband tops, which is characteristic of interference type filters. The need to have these filters carefully calibrated tends to make them a lot more expensive than normal color filters. The other application of special color filters is for astrophotography. Specifically, generating full-color images using a monochrome camera. To achieve this, the astrophotographer divides the visual band up into 3 color channels, red, green, and blue, using carefully designed filter sets. The most desirable of these filter sets are interference type, so as to have flat passband tops with high transmission values and sharp cutoffs with minimal overlap between filters. Bandwidths for the filters are selected to give complete coverage of the visual band, but also to keep subexposure times similar between the 3 filters. There are a number of advantages to creating a full-color image in this way, as opposed to using a one-shot color camera. Light pollution is reduced, since these color filters are effectively broad bandpass light pollution filters. With a monochrome camera, all of your sensor pixels are collecting data in each color channel, so you are able to take full advantage of the camera's resolution. Also, there is no extra Bayer matrix on a monochrome sensor, so you are getting the highest sensitivity versus the one-shot color version of the same sensor. These color filter sets are often sold along with a UV IR cut filter, also called a luminance or L filter. Since they are all interference type filters, they tend to be more expensive than typical color filters. The next category of special filters is meant for the correction of chromatic aberration. Different wavelengths of light bend or refract by different amounts in a glass medium, such as a lens. When designing a glass lens for a telescope or camera, this fact results in all the colors of light not coming to a focus at the same point, leaving the resulting image blurred by a violet, blue, and sometimes red fringe, especially noticeable on bright objects such as the moon. Centuries of lens design has struggled to correct this problem, culminating in the multi-element exotic glass apochromatic refractor. Apo refractors, however, are still expensive to manufacture, putting these high-performance telescopes out of the reach of many amateur astronomers. The more affordable runner-up in performance is the achromatic refractor, which, although better than a simple spherical lens, still has some chromatic aberration. When viewing bright objects like the moon or planets, this aberration is often visible enough to hamper viewing. The solution most commonly used is to add a filter that removes the unfocused violet-blue end of the spectrum. These filters commonly go by the name of fringe killer or minus violet. You will find that these filters are more effective when used during imaging, since camera detectors are more sensitive at the UV end of the spectrum than our eye. There is, however, a noticeable benefit to be gained using the filters visually. I have personally used the Beta fringe killer, that's the red line on the transmittance graph, with my 80mm achromatic refractor, and I can confirm that the filter does what its name suggests. If you are looking for a cheaper solution to chromatic aberration, try using a yellow Raton number 8 filter. That's the yellow curve on this plot. It should help. Using a chromatic aberration correction filter, you should be prepared for the fact that your view will have a yellow color cast. Depending on your specific telescope, the increase in sharpness and contrast may be worth the false color. A category of special filter that I have already briefly mentioned in part 2 of this video series is the neodymium filter. The concept of using neodymium, a rare earth element, to infuse the glass in an astronomical filter is somewhat serendipitous. The resulting glass media has multiple pass bands in the visible spectrum, and by some strange happenstance, the end result is a surprising increase in perceived contrast. These filters are available from a number of manufacturers, and they provide good contrast improvement with high overall transmittance. I personally use a moon and sky glow filter whenever I view planets or the moon visually. There are a number of variations on the basic neodymium-infused glass filter that tailor the filter for different applications. Some have interference coatings to provide UV-IR blocking, making them good for imaging. Some have additional blocking in the violet blue end of the spectrum to improve the performance of achromatic refractors. All in all, they are a curious family of filters that are worth having a closer look at. Note, however, that even though some manufacturers say that these filters provide light pollution reduction, the amount by which they do so is negligible. The last filter category to discuss in this presentation are those meant for solar observing and imaging. Astronomers have been looking for ways to safely observe the sun longer than they've been looking at the stars and planets. As a result, there are a number of different options available for use today. The main problem is that the sun emits a large amount of energy, not just in the visible spectrum, but in the UV and IR bands as well. In fact, only 45% of the solar radiation reaching our eyes is in the visible band. The simplest and probably the oldest method of safely viewing the sun is the pinhole camera, followed next by rear projection method using a small refractor. It wasn't until John Herschel came along in the 1830s with the idea of using a wedge-shaped piece of unsilvered glass to split off a small portion of the incoming sunlight from his telescope for safe viewing. The wedge prism splits off less than 5% of the incoming sunlight, dumping the other 95% out the back of the prism. The reflected 5% is then passed through a neutral density filter to reduce the light intensity to a safe level. This system now called the Herschel wedge, was further improved by Ignacio Porro by placing the glass wedge at an angle to polarize the reflected light, thus allowing a rotatable line polarizer to be added to give adjustability to the brightness. Herschel wedges are still available today, and many users, including myself, are convinced that they give the best white light views of the sun. Herschel wedges are truly white light, allowing for the use of additional bandpass filters in order to focus observation on particular parts of the visible spectrum. The main drawback of Herschel wedges is that all the sunlight is traveling inside your telescope, causing potential heating problems. They are therefore only suitable for smaller aperture refractors, less than 4 inches, and definitely not suitable for any type of reflector, be it Newtonian or Schmidt-Cassegrain. Another drawback is that Herschel wedges tend to be rather expensive, in the $500 to $800 range. Luckily, filter coating technology has come to the rescue of reflector and large refractor owners. The first aperture solar filters were made of absorptive glass, which removes 99% plus of the incoming sunlight. More recently, specially designed metal-coated mylar films have become possible because they are much cheaper than glass filters. These filters, sometimes called energy rejection filters or ERFs, are temporarily mounted over the sun-facing end of your telescope and can be full aperture, spanning the whole diameter of your objective, or off-axis, spanning only a small diameter circle to one side. Off-axis ERFs are usually recommended for larger aperture reflecting telescopes, say 6 inches or larger, as it removes the loss of contrast due to a reflector's central obstruction, the secondary mirror. And the effective increase in focal ratio helps reduce the appearance of atmospheric distortions. A big advantage of front-mounted ERFs is that they eliminate any risk of overheating inside your telescope. As with the Herschel wedge, narrowband filters can be added to white light solar aperture filters as well in order to improve the quality of the view. By adding a narrowband filter, sharpness and contrast can be improved, and more detail visible. The first, and perhaps best known add-on filter for solar observing is the Solar Continuum filter made by Bader Planetarium and also recently by Altair Astro. It centers on 540 nanometers, in the middle of the green part of the spectrum, where our visual acuity is best. Another add-on filter from Altair Astro that I like is the G-band filter. It passes a narrow band of light centered on 430 nanometers. It increases contrast and detail, just like the Solar Continuum filter, but also increases the visibility of faculae. To observe the sun's chromosphere, one needs to use a more complex filter system. These systems pair a specially designed ERF with an extremely narrow-band filter. The most common type of narrowband system focuses on the sun's hydrogen alpha absorption band, but there are also systems available for other absorption bands as well. Calling the H-alpha filter narrowband is an understatement. A narrowband H-alpha filter for deep sky imaging has a passband around 3 to 7 nanometers wide, while for solar observing they are more like 0.02 to 0.09 nanometers wide. Up to this point, I have been calling these devices filters, when strictly speaking they are not filters. They are etalons. Both function using the same principle of the interference of light, but implement it differently. As in an interference filter, light enters an etalon, passing from air into the optical media, for example glass, and partly reflects, partly refracts at the boundaries between air and glass. Some etalons use an air space between the semi-reflective coatings instead of a clear glass media. By carefully selecting the distance between the semi-reflective layers and their reflectivity, the etalon can be made to selectively pass a particular wavelength of light. The passed wavelength can be further adjusted by either varying the distance between the layers or by rotating the etalon relative to the incoming light. This is an important characteristic of etalons as it allows the observer to tune their etalon to account for wavelength variations in the H-alpha emission coming from the Sun. You maybe haven't thought about it, but the relative speed difference from one side of the Sun to the other due to its enormous rotation is on the order of 14,000 kilometers per hour. That's 9,000 miles per hour. This speed difference, plus that caused by the Earth's rotational velocity and orbital velocity, result in a wavelength shift up or down of the hydrogen alpha absorption line, a characteristic of light first predicted by Christian Doppler in 1842. As one can imagine, the precisely applied reflective coatings and ability to very finely adjust the spacing or orientation of the etalon makes these devices very expensive. Earth plus etalon packages for small aperture telescopes range in price from $800 to several thousand. The cost of buying these packages separately has made solar scopes, such as those from Lunt and Coronado, with the Earth and etalon fully integrated into the scope, another possible alternative worth considering. There is no doubt that these narrowband hydrogen alpha systems provide by far the best views of the Sun. Whether or not the view justifies the cost is a decision that you will have to make for yourself. If you would like to learn more about the equipment available to amateur astronomers for solar observing and imaging, stay tuned to the ARO channel for an upcoming video titled Supersizing Your Solar Setup that I plan to release soon. As I have quickly ran through in this video, there are numerous special-purpose filters available on the market today. Some are more useful than others, depending on what you are trying to do. Do your best to be an informed consumer. Read product reviews, ask questions on astronomy message boards. Be sure that the filter you are buying is right for what you are trying to achieve. That is it for Part 3 of Understanding Astronomical Filters. Part 4 on advanced filter topics such as extremely narrowband LP filters, star halos, and use with fast optics will be available soon. If anyone has any questions about this video or the other videos in this series, please feel free to leave a comment below. Alternatively, you can contact me by email using the address in my channel description. If you enjoyed this video, please leave a like below. To stay up to date on what the ARO is doing, please subscribe to the channel. This is Jim the Filter Guy, signing off.